Hello, welcome everyone. I think that's the first time I'm doing this talk in front of audience of this size. Anyways, glad you're here. That's not Dan's talk, by the way, in just in case you made a mistake. And I'm here to talk to you about location transparency. So let's start with who has heard the term before? Yeah, nobody, that's the case. That's the thing. Every time I ask this question, almost no one ever heard of it, and that's the reason this talk exists, right? So I'm going to be talking about that. My name, as introduced, is Milen Dyankov. I work for AxonIQ as a developer advocate, which basically means I go to talk to a lot of developers who are doing stuff and different solutions and try to help them or understand what they do so we can help them do stuff better or in a more productive way or any way we can. And I come from Poland, and okay, now I hope this works. Okay, yeah, it works. Now, this is my house, or it used to be my house. This is where me and my family used to live. And used to because at some point, we all used to love it there, but at some point in time, my wife started to feel not very comfortable. And then, I was like, I don't like the city. I like the beach. I like the seaside. Can't we leave on the seaside? And I'm like, no, not really. So after going a lot back and forth, we just decided there's a good solution. We're just going to get a piece of the house and move it on the seaside, right? And then that's where she lives. And she's super happy now because that's her dream place. And then I decided, okay, if she can do that, why I can't do my thing? Because I love mountains. I want to live in the mountains, sound very, very high with clean air, all those things. So, hey, we chopped another piece of the house, move it in the mountains, and this is where I live now. Kids are very happy because they're in the city. They can go to school, well, parties more than school, but everyone is super happy. The only tricky thing is when we go for a family dinner, we have to drive several hundred kilometers, but hey, come on, that's not a big deal. Did you buy that story? Man, it's ridiculous, right? Okay, give you another one. Here's my application, a beautiful monolith it used to be. Right? And it was working just fine up until some day when we decided that a piece of code needs to live somewhere else for whatever reason. And then a bit later, we decided another piece of code needs to live somewhere else. And then they somehow automatically will talk to each other. Much more believable, isn't it? Okay, the reason it's much more believable is because you and I and everyone don't seem to see all these interconnections behind the scenes. We just draw boxes and arrows, and then we assume that those systems will somehow communicate. They will somehow work together. But that's not the interesting thing here. When I was thinking about that analogy, what struck me is the ability of humans, of us all, to notice or not notice the nonsense, right? When I tell you a story about a house, you can immediately tell, yeah, well, that's bullshit, right? But when I tell you a story about a software system, most people go like, yeah, microservices, yeah, that's the future, right? So why it is that in some cases, we can immediately sense that this makes no sense. And in other cases, it's like, oh yeah, okay, it makes perfect sense, even though it doesn't. And I think it has a lot to do with this word, coherence. And more precisely, our ability as human beings to sense coherence in physical environments and everything that is about us and our things and our belongings. And to give you an example, now imagine you need to do a trip by a train, for example. And then you go to a train and they say, well, you board here, you sit here, but your purse and your coat and your hat will travel with a different train. Like, that would be awkward. Right? You would be like, no, it makes no sense. Like, my belongings travel with me, right? So we do have this sense of things being logically together. They belong with each other, right? And we can immediately tell if that is violated when it comes to physical things, but not so much about software. In software, we typically use another term, which is coupling. How many of you have never heard of coupling and decoupling? All right, never heard of it? Wow, interesting. I thought everyone by now is at least had one conversation about decoupling things, because it's becoming so popular topic. Well, coupling and decoupling is different from coherence. Coupling is when you get two things and you make them work together for some reason. Because it's more convenient, because it's more performant, because because it's faster. Right? They're purposely tied together. Think about the train analogy. The train cars are coupled. And they're coupled for the reason so you can put one engine in front, and it's going to drag all these cars behind it, no matter whether there's one car or 10 or 100. Right? That's the reason we couple them. But theoretically, you could decouple a train. You could put an engine in front of each car, and make them travel independently, right? And you're still going to achieve the same goal. You're still going to transfer passengers from point A to point B. You're just going to use 10 engines instead of one, or 15, or whichever amount of engines it takes. But the difference is it doesn't break coherence, right? Things are still coherent. It just It's just not coupled anymore. So there's fundamental difference between coherence and coupling. When we couple things, we can decouple them. When things are coherent, breaking them apart doesn't make a lot of sense. So let me talk about another term, which most of you probably haven't heard of, or at least that's my experience of doing this talk so far, and that is kinescence. How many of you have heard of kinescence? No, okay. So the first time I heard that term is when I read that book, Fundamentals of Object-Oriented Design in UML by Miller P. Jones. Trying to read from the slides. But that was a long time ago. And it kind of like, oh yeah, kinescence, whatever, right? But then many years after that, I kept getting back to that term. I keep discovering it in a lot of places. So if you don't know what it is, let me give you another example, still within the train analogy. So kinescence is essentially when two or more things have to do something together. They are not in a sense of coherence, not in a sense of we combine them this way, but because that they have some sort of interdependency. They've created with the idea of knowing of the other thing, and they're kind of bound to live together through the entire time they exist. And there is a kinescence, for example, between trains and railroads. Right? You cannot make the railroads wider and expect trains to still run. Right? And if you think about it, in terms of how those things are produced, they're different companies, different systems, everything's different. The infrastructure for producing railroads is different from that producing trains. They are not coherent, they are not coupled, but there is a connection between them. How you put the railroads depends on whether or not your trains will work. Right? So there is a kinescence between the railroad and the trains. It may not be obvious, and you may not think about it on an everyday basis, but it is there. Okay, enough with trains. Let's talk about software. So there is a very simple piece of code. It comes from an imaginary application written in Java that manages selling attraction tickets. You purchase a ticket for attraction. And there is a method in there that says, that accepts the attraction, right? And it assigns it to a field. Do you see any kinescence in there? Probably you don't, because you just learned what the term is, so let me help you out. What you see here is a kinescence of name. Now, the reason you have a kinescence is because you can't change the name of the field without changing the implementation of the method. If you do so, your code will no longer work. Right? Hey, another kinescence that you see in here is a kinescence of type. You can't change the type of the field without changing the type of the parameter of the method, because otherwise it will stop working. And the reason you don't see this and you don't think about this on an everyday basis is because we are at the point where we use IDEs and all kinds of software, of tools helping software developers, and they do this heavy lifting for you. You just go to your IDE, you say refactor, and it changes the names, and you don't even really care about it. It's going to find out where it is used, and it's going to change it for you. Therefore, these kinescences of type, of name, and a type is what we refer to as a low-level kinescence. We don't have to be worried too much about those, right? We can deal with those. If you only have kinescence of name and kinescence of type, it is a kinescence, but it's not really a problem. It's something that you can deal with. Okay, now consider this code. So on top, you have a list of attraction. And on the bottom, you have a code that calls that ticket thing and try to create a request to purchase not one but multiple like a ticket for multiple attractions. Any kinescence that you can spot in here? That one's a little bit tricky because it's called a kinescence of algorithm or kinescence of convention. And that is because in the method or constructor above, you make an assumption, or you have an algorithm, or you have a convention that the main attraction is the first of the list. Now, your code below, the code that is calling that code, needs to know that. Because if you were to put the main attraction last in the list, you're not going to get the behavior that you expect to get. Your main attraction will be something else. That may make a difference, may not. But it doesn't change the fact that these two pieces of code need to understand what's the algorithm or the convention or the assumptions behind the scenes in order to make sense, in order for the system to function properly. How about this? Let's fix that and just put a list of attraction and the main attraction as a separate field, as a separate parameter to the or argument, right? Is there a kinescence? Well, there is. It's called a kinescence of position, right? Because you can switch those in your call, and then your stuff stops working, and you will never know why. So again, the way you define things and the way things are being used by someone else, it requires both sides to have an agreement on something that's not explicit in either place, right? You cannot change one without changing the other, right? So I'm not going to go by all the existing kinescences. I think this is enough to illustrate the purpose, but there is also a kinescence of execution. That is when something needs to be executed for something else to make sense. Or a kinescence of timing, especially in, when you deal with real-time systems, like the two things needs to happen at the very same time or within a certain period of time. A kinescence of value is often one that we don't see but occurs. That means that something only works fine if something else has certain value. Right? And the kinescence of identity is very similar and whatnot. One that it's a little bit trickier is so-called the kinescence of difference or contrascence. And the reason it's trickier because it's the opposite. It doesn't naturally make it as a kinescence, but what it tells you is that by making choices of something, you are limiting yourself to making that choice a conflicting choice in the future. So if you call a method by ticket, right, you cannot have the very same method in the very same class. Again, you just taken away that choice from yourself, right? If you call a class something, you cannot have the same class in the same Java package. Right? And so on and so forth. So by picking a name, you are limiting yourself to never ever use that very same name for something else again. And that is a contrascence, because things may change and it may happen in the future that you would need that name for something else, but it's already taken. You can't use it because you're going to introduce breaking changes. That's essentially what contrascence is. And it doesn't apply only to names, by the way, but it's just easier to explain. So we have all these kinescences. And then we still talking about coherence and coupling. And the question is, how are those all together? Like, okay, why we have this? Is it because, like, should it be coherence instead, or coupling, or is it one driving another? It's neither. I think it's two different things, but there's a lot of similarities. I'm not sure if you're familiar with this book, The Domain-Driven Design, Eric Evans. It's one of the most popular books, I think, in software development world. But in that book, Eric Evans defines a thing called an aggregate. And an aggregate is a collection of objects which are considered to be one thing with respect to changes. Now, when you model a world of something, a domain, you can't typically model it with one object. It's, oh, that's my model, boom, one object. That doesn't work that way. You typically need more objects to model something. And those objects are somehow interconnected. But when you put them together and put boundaries within those and say, we treat that group of objects as something that is one thing with respect to changes, then you have an aggregate. And if you compare the definitions of an aggregate with those of what is a coherence, you will see quite a lot of similarities. We talk about the same unit or the unified whole, and we talk about boundaries and logical constraints, right? So that is essentially that is what is introducing a coherence, right? An aggregate with internally is expected to be very coherent. So how about kinescence? Now, because your aggregate, a group of objects, is very coherent internally, you can have high kinescence. Any kinescence that you can imagine within the aggregate is okay because you're treating that thing as a whole, right? And if something needs to change, probably the whole thing will change anyway, right? So within those boundaries, it's totally okay to have higher kinescence. Now, it doesn't have to be an aggregate. It could be just an arbitrary group of objects, as long as you can have a coherence boundaries around that, right? For as long as you can say those somehow guarantee those objects stay coherent no matter what, that's your boundaries. And then internally, you can have any kinescence, any assumption, any algorithm, anything you want, right? Because that's internal stuff. The tricky part is when you need to talk between those. Now, when you need to talk between those two contexts, then you really need a lower kinescence. Because if something changes here, then you're in trouble. Then your ability to evolve the system in the future is significantly limited. So how do you aim for low kinescence, but what does that mean? How do those things talk to each other? Well, they exchange data, right? One will create a data object or something and send it to the other one and vice versa. And that's on a high-level abstraction, right? I mean, even if you call a method, essentially that's what you do. You prepare a piece of data, and call a method, pass that data as an argument, and that eventually get another piece of data as a response, right? So no matter how you actually do this in technical terms, that's what happens. There is a piece of data that goes between those two groups of objects. And that's where my favorite part is about anything related to software diagrams is we draw boxes, or circles in this particular case, and we draw arrows in between them, and we go like, yep, those two will talk to each other. But how? How do they know how to talk to each other? How do they even know where one of the other is? Is there a kinescence of location? What these arrows mean? How that thing knows where that thing is? So let's talk about kinescence of location. That's not in the original book, but it's something that I repeatedly reach out to as a conclusion. So in that piece of code here, There is a kinescence of location, if you ask me. And that kinescence of location is because there is an assumption. And that assumption is that those two are in the same class. And we talk in the context of Java here. If you use other programming language, I'm pretty sure you can adapt it to your language. But in the context of Java, there is an assumption that the call to buy tickets and the declaration of buy ticket is within the same class. If you put those two, if you do a refactoring and put those two in different classes, manual refactoring that is, that code's not going to work anymore because there is an assumption they're in the same class. To fix it, you have to introduce a different class and then move the method there and whatnot. And then you have an assumption that those two classes are within the same package by the Java rules, right? If you put them in different packages, that code no longer works. Okay, well, that's easy to fix. We just add an import statement, right? I mean, come on. Well, yes, that fixes it for as long as both are in the same class path or module path on newer versions of Java. But there's again an assumption. There's an assumption that this code only works if those two are within the same JVM, on the same class path, or on the same module path. What if you want to go distribute it? What if you want to put this on a different machine? That code's not going to work anymore, and making it work, it's not that easy. Okay, let's go what people do. We're going to go REST, right? I mean, come on. We've been there. That's the reason, by the way, you see a lot of people going RESTful these days, is just to avoid this. When we need to scale now, we already can do this, right? We can do a request and response, and whether that's HTTP or some other protocol, it doesn't really matter. But now we have completely decoupled the two things, right? Well, not so much, because there is a requirement that these two things need to be configured in the same way. You still need to know where that server is. You still need to know what's the IP address or a DNS name or whatever the thing is, right? If you misconfigure one of those things, then things doesn't work anymore. Or if you choose to make an architectural change that thing's going to live somewhere else, you have to go and change all the clients, right? Because otherwise, things will not work anymore. And that is why people go like, yeah, okay, by the way, there's another kinescence here. That's kinescence of name. But as we said, kinescence of name is typically easy to say, to solve. Not so much in this case, though, because a lot of IDs are not really aware of the RESTful stuff, right, or the HTTP stuff. So it depends on what you're using, may or may not be easy to change. But there's also, in addition, a kinescence of name. And that's why a lot of people will say, okay, we go Kafka all the way, right? And then you just create a topic, and then you subscribe for a topic, and then you send to a topic, and that is one of the reasons why you see pretty much every software development company these days using Kafka in one way or another, because it's whole decoupled, distributed, and whatnot. And it introduces more or less the same problem. It's a kinescence by name, but it's now between 3 points. It's the name of the topic or the stream on the consumer, on the producer, and on the middleware, right? And even though it's technically a kinescence of name, it is not something that's easy to fix. Go change your topic name and see what happens, right? And there's no tooling that makes this easier for you, right? And all this is what I call location awareness. It basically means that a component needs to be aware where another component is, right? In order for these two components to communicate, one needs to know the location of the other or make assumptions about it, right? And so the question is, can we fix this? If we agree there is a kinescence of location, Can we fix this? Can we make systems discover each other somehow? And then I know you will say there's tons of discovery frameworks out there, but it's not the type of discovery I'm talking about, but more of a, can we eliminate the need of knowing where something is? I think we can. Let's focus on that data piece in the middle. So we just call it data because it was easier, but in most distributed systems, this will be called message. Some systems call it event. We'll see in a second why I don't like that word. But for the purpose of this talk, let's just assume these two things exchange messages. And now message is a fairly simple word, yet it means a lot of different things when you start digging into it. Those are messages. A command, me telling someone to do something, is a message. An event, me informing you that something has occurred, is a message. Me asking you what happened is a message. But those are three different types of messages. When you deal with commands, we typically want them to be sent to a single receiver. If I want to ask someone to bring me a water, I'm pretty sure I'm going to ask that person. I'm not going to go out and shout, "Someone please bring me water," right? It is typically one-to-one communication. And you don't typically require a verbose response to that. What you typically require is a confirmation, an ack-knack, I will, I want, right? But that's pretty much it. That's how communication works in terms of commands. Now, events are a different thing. Events are a notification that something has happened, and you want to notify the world or everyone interested that something has happened, so you want to shout it out loud. And you don't expect results. You just tell people, "Hey, people, this happened," right? That's it. You don't care what they think, whether they're going to do something about it or not. You let them know, and that's it. It's on them from that point on. So there is no response at all. But QRS is quite the opposite. QRS is the response is basically the only thing you care about. I mean, if you ask something a question, the only thing that you care about is the answer. If they don't give you an answer, it's pointless to ask them a question, right? So it's the same thing. It's message, message, message. But semantically, they are different. They are different in terms of distributions. They're different in terms of routing. They're different in terms of payload. So command is typically delivered to a single recipient, where events are delivered to all recipients, and queries may be delivered to one or many. But it also, in terms of the response, in commands, you basically just accept confirmation, and the events, you expect nothing. And in queries, you expect a full-blown result, right? And that could be very, very, very long result, right? So how you design a messaging system that works fine, and you just say, we just send messages, right? Because that's what Kafka does, like we just send messages. Right? So how you do this for these three different types of messages? So maybe there's a better way. Let's try to model this as Java objects. And it's going to be just a Java object that we call here a issue ticket command. And that's going to be a command. Basically, that represents our command that says, I want a ticket. Issue me a ticket. There's going to be an event that's called ticket issued event. Well, the ticket was issued, right? You know, the system completed its work, it's done deal, right? And then it's going to be a query, like give me the attractions in that ticket is for. And then when you define a query, you also want to define the response type, right? Because you expect an answer, so you better specify how that answer will look like. There's nothing special in this. It's just regular Java classes in this particular case. So what can we do with those? We could introduce a message router in the middle that understands these three types and that understands how to deal with them. And if we have such a router, what we can do is we can just send a command or a query or an event by using something like a bus or a gateway or something. So this is how it may look like. So, for example, we could get this thing called command gateway, which is used to send commands, and then you construct an object that is our issue ticket command, and you send that object to that command gateway and basically say, I want ticket, someone please issue a ticket for me. Or when you do, you can use this event gateway and say, yep, done, this just happened. Or you can use a query gateway and say, I want to know this, and then you still construct a plain Java object and you send it. So if you think about it, it's a few more lines of code, but conceptually, it's not different than calling a method, right? It's the same thing. It's just instead of calling a method, you use one of those gateways. But what it allows you to do is allows you to do the same thing on the flip side. You could have objects and aggregates or any coherent group of objects, and you can say, here it is, I can handle commands. I can handle events. I can handle queries, right? And then you subscribe or register yourself with this message router, which is simple enough, but yet intelligent enough to understand these three types of messages by doing something like annotations, for example, in Java. And you say, hey, I'm a command handler, and I can handle the issue ticket command. So whenever such command is received, route it to me. Or you can say, I'm an event handler, and I can handle this type of event. Or I'm a query handler, and I can respond to these types of queries. So it's declarative. You're basically saying, this is what I can do. So if any of this happens, route it to me. And then the message router in the middle knows how to do those. Like if you issue a command, you give me a ticket, it's going to route it to whoever can do that. If something happens here, it's going to send an event, and whoever is interested is going to receive that notification. And if a request is received, someone, one or many components that can answer that question can answer and provide a result. So, okay, I show you some code and how hard it is to actually implement this. Well, you would need two things. You would need that routing thing in the middle that is capable of doing that routing stuff, and then registering stuff, providing you those buses or gateways. And you would have something, you need something to do the actual wiring, like to allow you to transfer bytes of data between those systems. If you do, then it allows you to do higher kinescence within your components. Now, your components are the coherence boundaries, so within them, you can do whatever you want. You can have all the dependencies, all the assumptions, all the algorithms. It doesn't matter, because it's one logical thing with respect to changes. So whenever it changes, have to change it anyway. But because of the logical boundaries, nothing else needs to change, right? But everything that goes out of that boundaries is kinescence of name and type, as you've seen. It's basically, in Java case we saw earlier, it's a class name and a type, and that's it, right? So those become your API. Those because the thing that you don't really want to change very often, and you know that if you do, something will break, right? But now you know where the boundaries of coherence, where you can use high kinescence, and what is outside of those boundaries where you aim for a very low kinescence. Now you may be wondering, like, does such thing exist? Well, it does. It's called Axon Framework. And this is where I reach the point where I talk about our products, and which probably gives you an idea that we are by the end of the talk already. This is the problem we aimed for solving many years ago, and that's why the reason we created Axon Framework. And Axon Framework does exactly those things. It gives you the gateways, so you can and the message buses, so you can communicate between components, and it gives you the ability to subscribe or register components that can do different things. And it can be deployed as a single deployment unit. You just add the framework, and you deploy your great monolith, and you don't care. It works just fine. Configured properly in such scenario, it doesn't even gonna go do serialization and deserialization. So even though you technically using buses and gateways, there is almost no difference between doing a method call, because it all happens within the same JVM, right? But what if you want to go distributed? If you want to go distributed, that's a problem. Well, not really, because this is another product that we have. It's called Axon Server. It comes in two flavors. One is open source. The other one is the enterprise versions with a lot more features. And there's also a cloud offering if you're interested. But what it does is it's a dedicated solution for that messaging part. It also does different things. It can do event sourcing and whatnot, but that's not the topic of this talk. From messaging perspective, it does the very same thing, but distributed. So now you can put those in different deployment units and configure it to use Axon Server in the middle. And now your components deployed in a distributed architecture can talk to each other the exact same way they talked in your single monolith applications. So you don't have to change a single line of code in order to go from monolith to distributed. The communication happens the exact same way. It's just that in this case, you have to pay the penalty of serialization, deserialization, network transfer, and whatnot, because you are distributed, right? I mean, fallacies of distributed computing does not stop to apply just because we do this. But in terms of code, don't have to change anything. So I'll give you a brief descriptions of the three products that I'm referring to here. There's a lot more. If you want to learn about it, reach out to me in any of the, okay, here's my details, maybe that's better. In any of the ways you see here, we do actually created something to help developers learn about it, and that is the Academy, axonic.io. There are a bunch of free courses there. So if you do the free courses and you want to learn more, ping me. I'll give you access to the other ones. There is also a Discuss framework where you can ask anyone from our team about more information or how to do things. It's not about the products only, but also about design decisions and whatnot. Those are my details. Reach out to me anytime. Send your feedback if you like the talk. And that's pretty much all I had for you today, and I hope it was useful. And I want to thank you one more time for attending this talk. Thank you very much.